My name is Hunter Manning, and this is Lab 1 of Physics 2 at Georgia Tech, Charge Tapes. Before we begin, I'd like to briefly introduce what this report will be about. First, I would dive into the introduction of the lab. I would then identify important concepts. I would then explain the experimental model and then the computational model. I would then discuss the results and answer the assigned why and what if questions. This lab had three primary purposes. The first was to understand the interaction between charged objects. Second was to simulate these interactions computationally using GlowScript. The third was to predict the charge of the tape and the number of electrons lost or gained. Briefly touching on the results of this experiment, positive charges on tapes resulted in repulsion when they are near each other. Second, the electric charge of a single strip of tape was found to be 1.06 times 10 to the negative 8 coulombs. And finally, the tape was deficient with 6.65 times 10 to the 10 electrons. I will now touch on some of the important concepts of this experiment. The first is Newton's second law. This law states that the net force acting on an object is equal to the mass of the object times the acceleration of the object. In this, the mass is the mass of the piece of tape. Another important concept is Coulomb's law. This law states that the electric force is equal to K times Q1 times Q2 divided by the magnitude of the distance squared, multiplied by the unit vector. In this, K is a constant and Q1 and Q2 are the charges of the pieces of tape, considered to be equal in this lab. Another important equation relates force to the product of the charge and the electric field. Manipulation of this equation gives us an equation for the electric field, which is the result of dividing force by charge. One other thing that it's important to note is that F and E are vector quantities, meaning they have both magnitude and direction. Experimental model. In this lab, the system is tape B, which is the top piece of tape, and the surroundings are tape A, which is the bottom piece of tape. The tape has a mass of 2 times 10 to the negative 4 kilograms and a length of 2.07 times 10 to the negative 1 meters. The distance between tapes was found to be 2.28 times 10 to the negative 2 meters. Continuing with our experimental model, the magnitude of the force of gravity can be found by multiplying the mass of the object times the gravitational acceleration. In this case, the force of gravity was found to be 0.00196 newtons. The magnitude of the electrical force is equal to the force of gravity, which is also equal to 0.00196 newtons. To find the charge of tape B, I manipulated the electric force equation to equal the square root of the electric force times distance squared divided by K. By doing this, I found the charge of the tape to be 1.064 times 10 to the negative 8 coulombs. Now I just want to briefly touch on some important assumptions we made in this lab. The first was that the pieces of tape can act as point charges, and this was mostly used for the computational model to represent each piece of tape. The second was that we could ignore air resistance, and the final assumption was that each piece of tape has the same charge, evenly distributed about its length. Moving on to the computational model, all code was inputted into GlowScript. For the computational model, I incorporated Coulomb's constant, the acceleration due to gravity, the tape length, the tape area, the tape mass, the distance between the two tapes, and the charge of an electron. Further, I incorporated the equations discussed earlier in the important concepts section into the computational model to calculate the magnitude of the electric and gravitational forces, the charge of the tape, the number of electrons lost, and the ratio of deficient electrons to atoms. Results of this model are shown on the image on the right. These values match my calculations from the experimental model. The electric force on tape B due to tape A is depicted by the purple arrow, and the gravitational force acting on tape B is shown by the red arrow pointing down. Moving on to the discussion, based on the computational model, the charge was found to be 1.06 times 10 to the negative 8 coulombs. The computational electric force was found to be 1.96 times 10 to the negative 3 coulombs. Some potential sources of error include inaccurate measurements during the lab, accidentally touching the tape, which did happen, and rounding errors that happened during the experimental phase. Moving on to the what if and why questions. What if electrons had positive charge and protons had negative charge? In this fictional scenario, the observations would remain the same. The tape would still be attracted to opposing charges, as opposing charges are attractive to one another. The second question is, why is it important to handle the charged tapes as little as possible? Well, when you touch the charged tape, some charge is dispersed from the tape as you handle it more. Thus, the tape interacts with hands and loses some of its charge, which was also noted in lab as the more we touch the tape, the less it interacted with our hand.